Our next speaker, Ramtin Gharleghi. Ramtin is a research associate at UNSW with the Sydney Vascular Modeling Group, and he written a bio for me. His research focuses on improving segmentation of coronary artery, processing of large-scale coronary data sets, and efficient assessment of hemodynamic metrics, aiming to pave the way for improved predictions of cardiovascular disease risk. Thank you so much. This is Ramtin.
Thank you. My name is Ramtin Gharleghi. I finished my PhD a few months ago, supervised by Suzanne and Professor Arkansomia. So I'll be able to expound on the blood flow simulations on the coronary atlas that Suzanne mentioned. In particular, my research focuses particularly on wall shear stress. There are lots of dynamic metrics you can calculate. A lot of fluid dynamic metrics you can also calculate. Specifically for my research, I'm not particularly interested in the velocity or pressure and so on. We just consider the wall shear stress. It has generally been shown to heavily correlate with areas of disease progression. So if you can predict where the areas of low or oscillating wall shear stress are, that can help you identify patients that are at higher risk earlier before it can progress into an actual severe disease. In order to achieve this, we rely on CTCA imaging. We have routine CTCA imagings are routinely collected when people are referred for diagnostics. They're not particularly invasive. We use contrast enhanced CTCA, so you don't need to be injected with a contrast dye, but compared to alternative, this is a relatively non-invasive and routinely carried out procedure. Segmenting them can range from relatively easy to very challenging depending on the artifacts, the image quality, what sort of structures you have, and how and potentially abnormal the anatomy is. Based on the previous work we've done, we currently use a deep learning model to segment these arteries, and that shows reasonably good performance, at least for the areas we currently are interested in. So primarily, this is based on the ASOCO challenge. This is a challenge we ran at MICI 2020. It stands for Automated Segmentation of Coronary Arteries. We have a data set of 30 normal and 30 disease cases. We specifically chose that to have a balance of normal and cases with confirmed coronary artery disease. So when we develop coronary segmentation methods, we're confident that we can handle diseased cases. There's an automated evaluation framework at asoka.grandchallenge.com. You can also just look up ASOCA, and that is still functioning. You can download this data, develop your own segmentation methods, and you can submit it to the online evaluation. It will be automatically evaluated and tell you what the dice score and Hausdorff distance are and put you on a leaderboard for ASOCA. This data set is also publicly available if you want to use it for other research. You can use the CTCA and the manually contoured annotations for whatever you want, including commercial use cases. For the ASOCA itself, most of the submissions were based on N unit models. Since then, we've seen quite a few interesting publications using this data with much more sophisticated architectures. And then based on what we saw for this challenge, even in highly diseased cases and taking the worst segmentations among the 30 disease cases we have, it performs reasonably well, especially for the large main vessels. Having access to this segmented model, my research during my PhD mostly focuses on the left main bifurcation. Most of the blood flow passes through this bifurcation, and so it is generally clinically important. We also have the most amount of data available for CFD boundary conditions, and all the assumptions we need to make are fairly easily available for this bifurcation. So that minimizes the additional uncertainty we have both on the segmentation and on the CFD assumptions for this. Overall, we get CTCA images, we segment out the coronary tree, we extract the left main bifurcation, and then we run the CFD processing to get shear stress values for this. Over here, you can see a demonstration of the shear stress calculation. On the bottom, you have the flow rates versus time for one cardiac cycle, and it should show you shear stress values as you progress through the cardiac cycle. Areas that are consistently exposed to very low shear stress are generally believed to correspond to high risk of disease. There are also a lot of research into quantifying the geometry using various bifurcation angles and curvature of the vessels and so on, which we calculate and use for further processing. So this is all well and good, but actually calculating these requires significant computation time for the computation you just saw previously. It takes 30 CPU hours to actually calculate. You can run it with more cores and finish in less time, but it's still a significant computational burden. It will take several hours. It is not very accessible for actually large-scale studies. We can't monopolize the high-performance computing clusters we have available just to run these CFD simulations. So the way to address this is one of the ways is to try and use the developing deep learning methods to accelerate this process. We have a relatively fixed set of geometries, so deep learning can reuse information is learned over the training process, and we basically trade training time for the actual inference time. You can have much faster inferences using deep learning. In particular, we're using a neural network. The neural networks have been mentioned a lot today, but just as a brief introduction, you have several millions, and apparently with new large language models now billions of statistical neurons stacked on top of each other. Usually people say that these are inspired by biological neurons, but at this point it is more or less a very large statistical approximators where you have millions or billions of parameters to tune to get whatever behavior you want out of it. Neural networks exhibit two properties which are very important for our case. They are great at modeling nonlinear interactions, which is important in CFD. If you only have linear interactions, there are much better processes to use, but for CFD, we expect a lot of very complex nonlinear interactions, which would be well handled by a neural network. The second advantage is that you can pretty much learn everything implicitly. There are a lot of other CFD approaches like reduced order models and very large field of research to try and do similar things of speeding up CFD, but it is very difficult to incorporate all the interaction behavior you want into those models. Whereas with a neural network, you can generate a large enough data set and let the neural network learn whatever behavior you want implicitly, learn parameterizations of the space implicitly, and so on. Neural networks work most efficiently on 2D, at least convolutional neural networks. This statement is becoming rapidly less true as point clouds and mesh-based neural networks get more mature, but for the time being, I would still say this is the case where if you want highly efficient architectures, you would need a structured 2D data set to feed into your convolutional network. This is a problem for bifurcations because they're essentially unstructured 3D data. It is very difficult to try and coax this into a format neural network can work with. So in order to try and fix this, you can by cutting these into separate pieces. So you have 3 segments with 1 inlet and outlet, and then you can flatten all of pieces into cylindrical shapes, which are much easier to parameterize. If you have a cylinder, you can basically just cut it along a seam, and you will have a rectangular parameterization of the surface. This is a overall view of this remapping process. Use this to transform the wall shear stress that you're trying to calculate and any other geometric features you think are important. And you can remap everything into 2-dimensional rectangles, which are much easier to work with during using convolutional networks. And then we have a unit style model that's basically models features at several scales and then concatenates those at the end into a final prediction for what shear stress is. For this, we used 127 real patient cases. So if you're familiar with machine learning, very often you have some sort of data augmentation where you try and ensure your model doesn't massively overfit the data you have. For CFD, this is relatively easy because the ground truth generation is automatic. It just takes computation time. So you can deform the bifurcations you have and rerun them through the CFD process and get augmented data augmentation with fairly confidently generated ground truth. We only use this for training because if you use synthetic data for actually evaluating network, then you need to be a lot more concerned with if these are physiologically sensible and how much sense that makes. But we use it only for training. We test the network on only real cases, and that we can make sure we don't introduce any additional uncertainty into this evaluation. For each bifurcation, we generate 26 synthetic samples with different bifurcation and inflow angles, and we add those to the training set. And then at the end of this, you can get very accurate predictions of the wall shear stress in several seconds. The actual neural networks takes less than a second, but you need about a minute for all of this remapping and pre-processing required. But that is still much faster than actually trying to run CFD. Also, these are run on a CPU. If you actually had access to a GPU, then you could run the neural network predictions even faster. We have about a 4.36% error, which in the realm of CFD is actually considered pretty good. The CFD itself has reasonably high uncertainty in the same realm. Like you can't keep making the mesh finer and finer. So usually you make the mesh and time steps fine enough to accept about a 5% error. At this point, we're reasonably happy with the performance of this model. It has uncertainty somewhat comparable to actually doing CFD simulations. On the left, you have the ground truth generated from CFD, and on the middle, you have the network's prediction. And on the right, you have the error between these two predictions. For calculating risk scores, it's a lot more subjective. A lot of people will take the shear stress and use some sort of threshold, like they'll consider shear stress below 0.5 pascals to be indicative of disease risk. So if you want to that sort of analysis, this sort of machine learning approach still predicts risk scores fairly well with significantly lower computational time. Out of time, so in the future, we're hoping to expand this and continue validating if the risk scores we calculate will actually correspond to a higher risk of disease in new cases. Thank you. If you have any questions, I will answer those.
Thanks for the talk. Just for the last thing you mentioned, where you were hoping to see if you could validate it against stuff. I think earlier your colleague mentioned that they have follow-up scans. So you've had some patients in your cohort of CTs that have already had a scan once and then had a follow-up scan a number of years down the line. Have you tried it out looking at those, comparing your data with those follow-up scans?
Yeah, that's something we're in the process of doing. I think you can, I think that's called the GeoCat project. You can look up the publication on that if you want more detail, but we're currently in the stages of gathering all data, making sure we can process them without getting access to follow-up data and mortality has much more restrictive ethics conditions than these sort of structures. So we're still in the process of making sure we can do all of this following our ethics restrictions. And yeah, we haven't actually ran these on data we have and respond to the mortality.
Great. More questions? Yeah.
Thanks for the talk. I was just interested in the process that you're using for taking your cylinder and then flattening that out. That looks to me like you're throwing out a lot of information because it's not truly just a straight cylinder in most instances, right? So how's your modeling including that information in that process?
Yeah, so this is one of the reasons I mentioned I like using neural networks for this. You have the cylinder used as the grid for the neural network to compute values, but you can actually feed in the coordinates, positions, and surface curvature and torsion and so on. And it's up to a neural network to try and adjust for the additional information it needs to. For the actual parameterizations, you can construct this sort of coordinate systems, and you basically cut out the cylinders and you align everything. The choice of the coordinate system you use is somewhat arbitrary, but you can align everything using this central line-based coordinate system, and then leave the neural network to figure out how to model the potential issues it has. And this 4.3% figure mentioned is after remapping everything back to an actual bifurcation. So despite any additional error introduced, it still performs reasonably well. There are some more analysis of this in my thesis that I don't remember the exact values of, but I went through what sort of grid sizes I would need and what interpolation methods are needed to minimize the error introduced from this remapping to a grid and back to a bifurcation process.
Okay. Any other questions? All right. Thank you again.